Good morning, students. Last class we were discussing about the different characteristics of particles of matter, and now in this class we are discussing about the different states of matter. Different states of matter. So, different states of matter. You know, normally matter can exist in three states, that is solid, liquid and gas. These are the different states of matter. Matter can exist in other forms also, that is plasma state is this, then Bose-Einstein condensate, etc. So, different states are there, but generally normally a matter can exist in three states, that is solid, liquid and gas. Now, let us see how the particles are arranged in these different states of matter. So, let us discuss one by one. First one is solid state. So, we have studied that is in the last class, that is what are the characteristics of particles of matter. So, the first one is the particles of matter, they are very small, isn't it? They are very small. And even though if they are very small, how they are arranged inside these different states of matter. So, in the solid state, for example, if you are taking this is a solid, and inside this the particles are very closely packed. The particles are very, if these are the particles, if you represent these are the particles, then they are very tightly or closely packed. So, since they are tightly packed or closely packed, there is no intermolecular space, that is they hardly have intermolecular space, or it means it is negligible. The intermolecular space or interparticle space is very less or negligible in the case of solid. So, if there is no space between the particles, they are what? They are hard and rigid. They will be hard and rigid. So, the first one, if you are just listing out the different properties. So, first one is in solid state the particles are closely packed. They are closely packed. Then the second one, since they are closely packed, the interparticle distance is very less. So, the space, interparticle space between the particles are negligible, or there is no space between the particles, or there is no intermolecular space between the particles. And then, as I said, since the particles are tightly packed, they are rigid, they are having rigid, and then they show rigidity. And see, if we take many types of substances, for example, if we take if this is a solid particle. So, when we draw an outline, with a pencil or any other substance, here I am drawing with a chalk. So, you can see there is an outline is there. It means that they are having shape, they are having a particular shape, isn't it? They are having a particular shape, and they also have a particular volume is there. So, they show definite shape and definite volume, isn't it? Definite shape and volume. So, they are having definite shape and definite volume. Then see, here I have taken a duster. Instead, if you are taking a pen or any other substances, a notebook, so all these are having a definite shape and definite volume is there, isn't it? So they are having definite shape, definite volume, they are showing rigidity, they have a space, the space between the particles are very less or it is negligible, and they are closely packed. And then the another property is that these solids, what about their diffusion? So diffusion, I think we studied in the last class, that is what is diffusion? The intermixing of particles, the intermixing of different particles of matter by their own, that is called a diffusion. So the diffusion is very less in the case of solids. Diffusion is very less. Why? Because the particles are not free to move, they are closely packed, they are tightly packed, so the particles cannot move from one place to another place. So the diffusion is very less. But in certain cases, for example, solids like camphor and dry ice, they show diffusion because they are sublimable substances. What is sublimation and all? I think you have studied in lower class. Anyway, we will discuss what is sublimation. So these substances, they show diffusion. Only few substances, but most of the solids are they are what? They will not show any type of diffusion. There is no diffusion. The diffusion is very less in the case of solid state. So these are some of the. What about the another property? You can also explain about the density. The sixth property is density. You know what is density? Density is mass by volume. Mass by volume. So the density of solids are somewhat higher, isn't it? The density of solids are somewhat higher because they are having, since the particles are very closely packed, the number of, that is mass per unit volume will be high in the case of solids. Then another property is that what about the compressibility? Compressibility. Whether solids are compressible or not. Solids are compressible or not. That is, whether we can compress the solids. They are less compressible. Why? Because since the particles are closely packed, there is no space between the particles, and that's why they are less compressible or incompressible. But some solids like sponge, sand, etc., they are somewhat compressible. Why? Because in these particles, air is present in this type of particles, but when we compress, the air particle will expel out. So at that time they are compressible, isn't it? So only few particles are compressible, but most of the solids are less compressible. So these are the different characteristics of particles of matter in the solid state. So they are, since they are closely packed and the space, the interparticle space is very less, and they are rigid. And then they are showing definite shape and definite volume, and then they are some are what they show in definite shape and definite volume, and they are less, that is diffusion is very less. The diffusion is very less in the case of solids, but some solids like camphor and dry ice, they are somewhat they showing diffusion, and then about their density is high in the case of solids, and then compressibility, they are less compressible, but certain substances like sponge, sand, etc., they show compressibility. So these are the different characteristics of particles of matter in the solid state. Now we move on to the next another state, that is liquid state. In the liquid state, so in the liquid state, what about the packing? The packing of these liquids, how the particles are arranged in liquid state. In liquid state, the particles are loosely packed as compared to solid. As compared to solid, they are loosely packed. So here we can represent the close packing in this is solids, but in liquids they are somewhat loosely packed. They are loosely packed. But as compared to gases, they are somewhat closely packed. So here the particles are loosely packed, and then what about the intermolecular space? The intermolecular space are large as compared to solids, but less as compared to gases. Then what about the rigidity, whether they are rigid? No, they are instead of rigidity, they show fluidity. They show fluidity, or they can flow. They can flow. For example, if we take same amount of, that is for example 50 ml of liquids such as oil, water, milk. So you take different liquids like oil, water, milk, etc., in different containers, and then you spill that liquids on the floor. So whether after spilling, whether they flow, yes, they will flow through the floor, isn't it? They will flow, or they can have an ability to flow, that is called fluidity. So liquids, they will flow, they show fluidity instead of rigidity. In the case of rigidity is in the case of solid, and they show here liquid state, they show fluidity. And then what about shape and volume, whether liquids, they are having definite shape and definite volume? No, liquids, they do not possess definite shape and definite shape, but they show definite volume. They have not definite shape, but they possess definite volume. How can we prove this, whether liquids possess definite shape and whether they possess definite shape, or they possess definite shape, and why they are showing a definite volume? So take different that is different apparatus, like for example this is conical flask. This is called a conical flask. So the shape of the conical flask is like this, and then another container we are taking. This is called this is conical flask, and this is called RB flask. That is called round bottom flask, RB flask. Then take a beaker. This is a beaker. So, all these are graduated measurements. Graduated means they are showing different that is their values, that is 50 ml, this is 100 ml and 150 ml, etc. So, graduated apparatus we are taking. In these apparatus we take equal amount of water. For example, we take 50 ml of water in all these cases, 50 ml of water. So, when we take 50 ml of water in what, this is beaker, this is beaker. So, when we take 50 ml of water in beaker, so that will take the shape of that beaker, that 50 ml of water will take the shape of beaker. And when we pour the same quantity, that is 50 ml of water into conical flask, it will take the shape of, so the shape of that water will be the shape of conical flask. And when we take the same amount of water in RB flask, so that will be in another shape, isn't it? It means what? They will take the shape of, the liquids will take the shape of the container. When we take the same amount of water in boiling tube, it will have the shape of boiling tube. So, liquids they take the shape of the container, they do not have any definite shape, but they are having definite volume, isn't it? They are having definite volume, isn't it? Because we take same amount of water, so that same amount of water will be there in all containers. So, they have definite volume, but no definite shape. And then what about diffusion? In the case of liquids, they are having more power of diffusion than solids, because they are, since they are loosely packed as compared to solids, they are having more diffusion. They are having more diffusion power. And the volatile liquids means they are easily vaporizable liquids. For example, petrol, then this one, diesel and alcohol, ether, etc. All acetone, alcohol, ether, all these they are called volatile liquids. They are easily vaporizable. They when we pour some petrol in our palm, after few minutes it will disappear, that is called volatility. So, when we take volatile liquids, they are having more diffusion, they are having more power of diffusion, and the other liquids, they are showing less diffusion as compared to solids. As compared to solids they are more, but as compared to volatile liquids they are having less diffusion power. So, they show more diffusion as compared to solids, but volatile liquids they are having more power of diffusion. And then the density is, if we are comparing the density of liquids, they are less having less density as compared to solids. Then compressibility, these liquids are somewhat more compressible than solids, but it is less compressible than gases. So, compressibility is less in the case of liquids as compared to solids, they are more compressible, but as compared to gases, they are less compressible. Then, so these are the different properties of liquid state, and then we move on to the next state, that is gas state. Gas state. So, in gas state, what about the arrangement of particles? That is whether they are closely packed or loose. They are loosely packed. They are loosely packed. The particles are very loosely packed. They are having more freedom. The particles are having more freedom to move. So, they are loosely packed. Since they are loosely packed, the force of attraction between the particles are very less. The force of attraction between the particles are very less, and also the space, intermolecular space is very large. It is very space between the particles are, the space between the particles are large space. There will be large space between the particles of matter, and they are loosely packed. They are loosely packed. And what about the fluidity? The fluidity, they also shows fluidity, or they can move from one place to another place. So, they are also showing fluidity, and so they are easily move. They can move from one place to another place. And what about their shape and volume? They do not have any definite shape and no definite volume. No definite volume. They are they do not have any definite volume, and then they do not show any definite shape and definite volume. And what about the diffusion? Gases are more, they show more diffusion than solids and liquids, isn't it? And that's why, and the rate of diffusion increases with the increase in temperature. The rate of diffusion increases with the increase in temperature. That is why, when we press any spray, the spray reaches, that smell will reaches quickly in summers than in winters. Why? Because the rate of diffusion increases with the increase in temperature, and so gases, they show more diffusion than solids and liquids, and the density is very less as compared to solids and liquids. And compressibility, they are highly compressible. They are highly compressible, and that is why, since they are highly compressible, we know the cooking gases, that is LPG and CNG. LPG and CNG, that is liquefied petroleum gas, compressed natural gas. CNG means compressed natural gas. This is liquefied petroleum gas. So, the gases under high pressure, because since gases are compressible, we can compress them under high pressure, and that large amount of gases can be compressed, that can be occupied in a smaller cylinders or smaller containers, and that is why gases are compressible, and that's why they are using in LPG and CNG. That is due to the property of compressibility. Compressibility is more in the case of gases. So, these are the comparisons between solids, liquids and gas state. So, they are how the particles are arranged. The particles are very loosely packed in the case of gas state, and since the particles are very loosely packed, the intermolecular force of attraction is very less. They are free to move, and then when we take some amount of gas in a container, for example in a balloon, so the particles, the gas particles inside the balloons they are free to move. So, they will move randomly all over the space available to them, and then they will occupy all the space available to them. So, and then when they move in a container, they will strike the walls of the container, and when they strike the walls of the container, they exert some pressure, they experience or they exert some pressure on the walls of the container. So, that is why, because they are in a random motion, they are free to move, the force of attraction between the particles are very less. and they also show fluidity because the particles are loosely packed, and then they are not showing any definite shape and definite volume. And some cases, for example balloon, when we take some air, when we inflate a balloon, so inside the balloon air is there, so that air is having a shape of balloon, so different shaped balloons are there. At that time only it is having a definite shape. So normally they do not show any type of definite shape and definite volume. And then the rate of diffusion is more in the case of in the gases, and the rate of diffusion increases with the increase in pressure, increase in temperature. As the temperature increases, the rate of diffusion also increases, and the density is very less in the case of gases. And compressibility, they are highly compressible, gases are highly compressible, and that is why gases are used in LPG and CNG. Okay. Now, then we move on to the next topic, that is measurement of temperature. Measurement of temperature. So what is a temperature? Temperature is the degree of hotness or coldness, isn't it? Temperature is the degree of hotness or coldness. And normally we measure the temperature, the different scales available for measuring the temperature are degree Celsius, as we represent like this, degree Celsius, and then Kelvin scale. Kelvin, it is represented by K, and then Fahrenheit. Fahrenheit scale, that is represented by degree Fahrenheit. So degree Celsius, Kelvin scale, and Fahrenheit. So normally these two are, we are considering degree Celsius and Kelvin scale, and the SI unit of temperature is what? It is Kelvin. K, it is represented by K. The SI unit of temperature is Kelvin. Okay, Kelvin. Now, in this class we are going to study how can we convert degree Celsius into Kelvin scale and Kelvin scale into degree Celsius. So what is the relation between these degree Celsius and Kelvin scale? So we can represent Kelvin scale is equal to degree Celsius plus 273. Kelvin scale is equal to degree Celsius plus 273. So from this we can also calculate how we can calculate degree Celsius. So degree Celsius is equal to K minus 273. K minus 273. Degree Celsius is equal to Kelvin scale minus 273, and Kelvin scale is equal to degree Celsius plus, so you have to add 273 plus degree Celsius in order to get Kelvin scale. So these two are the important relation between degree Celsius and Kelvin scale. So based on this we can do some numericals. Okay, we can do some numericals, and there is a Fahrenheit scale we can also represent like this, that is Fahrenheit is equal to 5 by 9 by 5 degree Celsius plus 32. That is the relation between degree Celsius and Fahrenheit, but we are not going to discuss this one. Okay. Now we are going to discuss some of the numericals, how we can convert degree Celsius into Kelvin scale. If the temperature is given in Kelvin scale, how can we convert into degree Celsius, and if the temperature is given in degree Celsius, how can we convert into Kelvin scale. So, the first one, convert the following temperature into degree Celsius. Convert the following temperatures into degree Celsius. Convert into degree Celsius. So, the question is given, first one, 300 Kelvin. We have 300 Kelvin, and second one 573 Kelvin, and third one 298 Kelvin. So, convert these temperatures into degree Celsius. Degree Celsius. So, we have studied that degree Celsius is equal to K minus 273. K minus 273. So, how can we convert this? So, in order to convert 300 Kelvin into degree Celsius, what we do? That is 300 minus 273. 300 minus 273, that is equal to how much? It is 27 degree Celsius. So, 300 Kelvin is equal to 27 degree Celsius. And what about here? That is degree Celsius is equal to 573 minus 273. That is equal to 300 degree Celsius. 300 degrees Celsius. And what about here? 298, that is degree Celsius is equal to 298 minus 273. That is equal to 5 and 20. So, 25 degree Celsius. So, 298 Kelvin is equal to 25 degree Celsius. And in some case, degree Celsius may be given and you have to convert into Kelvin scale. How? For example, if this is degree Celsius, all these are degree Celsius, then convert this degree Celsius into Kelvin scale. So, how can we convert into Kelvin scale? So, Kelvin scale K is equal to degree Celsius plus 273, isn't it? Plus 273. So, it means 300 means 300 plus 273, that is equal to 573 Kelvin. And 573 into Kelvin scale. So, 573 plus 273. That is equal to 6, 4, 846 Kelvin. Then here 298 plus 273, that is equal to 11, 8, 7, 571 Kelvin. 571. So, in order to convert degree Celsius into Kelvin scale and Kelvin scale to degree Celsius, so this relation, you just remember this relation, that is Kelvin scale is equal to degree Celsius plus 273 or degree Celsius equal to Kelvin scale minus 273. Okay. Next topic is interconversion of states of matter. Interconversion of states of matter. That is, matter can be changed from one state to another state. That is from solid to liquid, liquid to gas, and gas to solids, etc. So, there is interconversion of the states of matter is possible. Can it possible? Is it possible or not? And during this conversion, what are the changes is taking place to the particles? The particles of matter. What changes are undergoing to these particles of matter when there is a conversion from one state to another state? So, what is happening there, that we are going to discuss. And here if we take water as an example, or water exists, normally water exists, the different states of water are, water exists in 3 states, that is the solid state as ice. Water exists as ice as in the solid state, and they exist as water in the liquid state, and they exist as water vapor in the gas state, isn't it? They exist as ice solid state, and liquid state water, and water vapor as gas state. So when we take a beaker, and take some pieces of ice cube, take some ice cube inside this ice cubes, and then you heat by placing on a tripod stand. You heat this ice cubes, and also you insert a thermometer in which the bulb of the thermometer is in touching with the ice cube. Then on heating, the particles, that is ice cubes, they start melting after some time. After when we are heating, on continuous heating, it will melt. The ice cubes will melt, isn't it? So at that time, when ice cubes are melting, you note that, so initially note the temperature of the thermometer, and after heating, when the ice cube starts melting, you also notice the temperature. So, and when all the ice cubes are melting, and it is found that the temperature of the thermometer remains the same. So that is happening here. So what is the reason for this? What is happening here? When we are heating, what is happening to the particles of matter? So in the case of ice cubes, we know the particles, since ice is a solid, the particles are very closely packed. When we are heating, so they are getting more kinetic energy. When the particles are in the solid state, they are not free to move because they are tightly packed, they are closely packed, and there is no space between the particles. And then when we heat, they are getting more energy, the more kinetic energy to move. So they will they will get enough energy to break the force of attraction between the particles. When we are heating, that heat energy, by absorbing the heat energy, the solid particles are getting enough kinetic energy to move or to break the force of attraction between the particles, and at that time they will start melting. So what is melting point? That melting point is the temperature at which a solid starts changing into, or solid melts into liquid state at the atmospheric pressure. It is the temperature at which a solid starts changing into liquid state at the atmospheric pressure. That is called a melting point. And the melting point of ice is found to be 273.15 Kelvin, or 273 Kelvin. 273 Kelvin is the melting point of ice. So here the ice particles are changing their state, that is from solid to liquid state. So when they change from solid to liquid state, here the process of heating is continuing. So at that stage, even though if you are continuing to continue the heating process, there is no rise in temperature in the thermometer. There is no rise in temperature in the thermometer, or the temperature remains the same, that is 273 Kelvin. There is no rise in temperature even though if we are heating. So where does this temperature goes? Where does this temperature go? That is the extra temperature, because here they are all the ice cubes starts melting. At that time the temperature remains same. So even though if you are heating, the temperature remains the same. So where did go this extra temperature? Where did go this extra temperature? So that temperature, that extra temperature is utilized for changing the state. That extra temperature, that extra heat is utilized for, that is that heat is absorbed by the ice cubes or solid particles, and they utilize that heat for changing their state, that is from solid to liquid state. So that temperature is hidden inside this solid particle, and that is why that temperature is called latent heat. That is called latent heat. That is called latent heat. That hidden temperature is called latent heat. So I told you that what is melting, that is what is melting point. So melting is also known as fusion. It is also known as fusion. Melting is also known as fusion. So here the temperature of the substance remains same if we are heating. So here the solid particle, that is ice cube, starts melting. So at that time the temperature remains same, there is no rise in temperature. So that temperature, at that time the temperature remains same even though if we are continue to heat. So where that extra temperature is going? That temperature is used for changing the state of the matter, that is from solid to liquid, and that temperature is hidden inside the solid particle, and that temperature is called latent heat. Latent heat. And what is called latent heat of fusion? And can you define what is latent heat of fusion? So latent heat of fusion means it is the minimum temperature or the temperature required to change 1 kilogram of a solid substance It is the temperature required to change 1 kilogram of a solid substance into liquid at its melting point at the atmospheric pressure. At its melting point at the atmospheric pressure. That is called latent heat of fusion. It is the amount of heat energy required to change 1 kilogram of a solid substance into liquid at its melting point at the atmospheric pressure. That is called latent heat of fusion. Latent heat of fusion. Okay. And then if we again, so after completing if all the ice cubes are converted into liquids, so now in the beaker, if it is a liquid, it's a water, okay, it's a water. Again we are dipping one thermometer, the bulb of the thermometer is dipped inside they are in touch with the water, and then again we are heating. Now we are heating water, that is in the liquid state, water. Then when we continue to heat, we know that here when we continue to heat the water molecules, the water after a particular temperature, after reaching a particular temperature, the liquid or water molecule begins to boil. So at that temperature, when we heat, again on heating, the water molecules begins to boil, and then at that time again the temperature, it is seen that the temperature remains same, that is 100 degrees Celsius or 373 Kelvin. At this temperature again the water remains same. So where this extra energy, when they starts boiling, at that temperature there is no further rise in temperature. The temperature remains the same at a particular temperature. So that temperature, the temperature at which a liquid starts boiling at atmospheric pressure, that is called a boiling point. The temperature at which the liquid starts boiling at atmospheric pressure, that is called a boiling point of that liquid. So the boiling point of water is what? 100 degrees Celsius or 373 Kelvin. So when that stage is reached, again if we are heating, there is no rise in temperature, the temperature remains same. So where did this extra temperature go? So that is that extra temperature or extra heat energy is utilized for changing the state from liquid to gas, So that temperature is absorbed by the water molecules, and that is hidden in the water molecules, and that is called a latent heat. But here instead of latent heat of fusion, here latent heat of vaporization, because liquids they converts into gases, that is called vaporization. So that is called a latent heat of vaporization. So what is latent heat of vaporization? It is the amount of energy or amount of heat energy required to change 1 kilogram of a liquid into gases at its boiling point in the atmospheric pressure, That is called a latent heat of vaporization. Okay. So that's all about the latent heat of fusion, latent heat of vaporization. So during the change of state from one state to another state, so at that time if we continue to supply the heat energy and there is no further rise in temperature is happening, so where this extra energy is gone, that is called a latent heat, because that extra energy is utilized for changing their state from one state to another state. Because we know in between the particles there is a force of attraction. So in order to break that force of attraction, this extra energy is utilized. That is why it is called latent heat. And in the case of solid to liquid, it is called latent heat of fusion, and in the case of liquid to gas, that is called latent heat of vaporization. So I hope you understood all these concepts, and we will discuss in the next class. Have a nice day.